Welcome to Brain Vision.
All right, so the first thing we do for this problem is draw out a diagram. So we're given that we have a platform that has two springs that are parallel to each other. So let's draw that then. So if the springs are parallel, we could just draw one spring on top of the other spring like this. Okay. And we could assume that each of these springs has a different spring constant. So we could say the top one has a spring constant of K1, and then the bottom spring has a spring constant of K2. And then we're going to be pushing on this platform with some force. So we're going to call this force F. And then this force is going to compress these two springs here. So we're going to draw this platform, but then have it be compressed a distance x. So these springs are going to be moving a distance x here from their equilibrium position. Okay. And then since these springs are in parallel, that means we actually add the two spring constants together. So we can add K1 and K2 together to get their equilibrium spring constant. So if we add K1 and K2 together, we get their equilibrium spring constant, which we just call K. Okay. And since we can do this, we could just imagine we have these two springs as one spring then. Because if we add them together, we get one spring constant. So we could just redraw this with one spring. So this one spring is going to have a spring constant of K, where again, K is just K1 minus, or K1 plus K2. Okay. So now we have a diagram to show what's going on. Let's go and solve the problem. So we're given that the work needed to compress the spring 0.2 meters from the uncompressed length is going to be 80 joules. So work is going to be 80 joules to compress the spring. And the spring is being compressed 0.2 meters. Okay. So that means that we're given the work So we're given that the work is equal to 80 joules. And then the spring is to be compressed, the distance x here. So we're given that distance, which is 0.2 meters. Okay. So we're given that in the problem. Now for part A, it's saying what is the magnitude of the force you must apply to hold a platform in this position? Okay. So we have to solve for this force F here. So we're trying to find F. Okay, and then again, this is part A. So we're trying to solve for this force here. Now we have equations that we can use to solve for this force. So we know the force to compress a spring is going to be equal to K times X, where K is the spring constant and X is the distance it's being displaced. Okay, and we also have the work to compress a spring. So that's going to be equal to 1/2 kx squared. Okay, so now we're trying to solve for what F is because we want the force. So we're given X, but we don't know K. But we can use the work equation here. So for the work equation, we're given W and we're given X, so we could solve for what K is. So then if we know K, we could plug in the value for K in the force equation and then solve for the force. Okay, so let's do that. So let's use the second equation here and then solve for what K is algebraically. So let's just rearrange this equation to solve for K. So if I do that, I'll get K is equal to 2W divided by X squared. So I'm just rearranging this equation with W to solve for K. Okay. And now I can plug in the values that I'm given. So the work is going to be 80 joules. And the displacement X is going to be 0.2 meters. Okay. And now I can plug this into a calculator. I'm going to get 4,000. So that's the number I get. But let's just keep on the units here. So for the units, I have joules divided by meters squared. Okay. And I know that a joule is going to be newtons times meters. So I'm going to have 4,000, and then the units are going to be newtons times meters divided by meters squared. So then the meters cancel out in the numerator, and then the meters squared just becomes meters. So I'm going to have 4,000 newtons per meter for the spring constant K. Okay. So now the spring constant K, so I can solve for the force F now. So I'll plug in K equals 4,000 newtons per meter. And then I know my X value is going to be 0.2 meters. So then if I plug this into a calculator, I'm going to get 800 newtons. So the force needed to cause this displacement of 0.2 meters is going to be 800 newtons. Okay, so that's part A. Now for part B, it's saying how much additional work must you do to move the platform 0.2 meters further, and then what is the maximum force you must apply. Okay, So let's start on the page here. So this is part B. So it's saying it's going to move 0.2 meters further than it did before. So the x value was 0.2 meters before, and now it's moving 0.2 meters further than that. So that means the new x value is going to be 0.4 meters. So I'm just doing 0.2 plus 0.2. So we're given that the new x value is going to be 0.4 meters. So it's being displaced 0.4 meters now. Okay. So what are we trying to find? So we're now trying to find the additional work that you must do to move the platform 0.2 meters further. Okay, so we're trying to find the work. So I'm going to call this W again. Trying to find W. And then also, what is the maximum force you must apply? So we're going to try to find the force needed to compress the spring 0.4 meters. So we're trying to find force F again. But now our X value is going to change. Okay. Okay. So let's start with the additional work, W, first. So it's saying the additional work. So what we can do is to calculate this work here, we could take the final work minus the initial work. So the initial work is going to be when the spring has been compressed 0.2 meters, and then the final work is going to be when the spring is compressed 0.4 meters. So that's the case in part B now. Okay, because we want the additional work with the extra 0.2 meters. Okay, so I'll just write that down here. Okay, so again, the initial work is when the spring is compressed 0.2 meters, and then the final work is when the spring is being compressed to 0.4 meters. And we're doing this because we're looking for the additional work that you must do to move the platform the additional 0.2 meters further. Okay. So now we know the initial work here. So the initial work we could actually use, we're given in part A. So in part A, the work needed to compress the spring 0.2 meters is just going to be 80 joules. So we already know Wi here. So Wi is going to be 80 joules because we're given that in part A. Okay. And then the final work, Wf, we could just calculate that using the work equation. So we're just going to use 1/2 kx squared again. Okay. And K is the spring constant. So the spring constant is a constant value, which means it doesn't change. So it's just a property of the spring. So if we calculate the value of K, that's always going to be the case. It's never going to change. And then if we're compressing the spring 0.4 meters, our X value is going to be 0.4 meters then. So we could just use, so to calculate WF, we could use the K value we calculated in part A. So it's going to be 4,000 newtons per meter. And the next value is 0.4 meters. So then if I put this in a calculator, I'm going to get 320. And let's keep an eye on the unit here. So we have newtons per meter times meters squared. Okay. So then this meter squared becomes a meter, and then the meters in the denominator cancels out. So then I'm just left with newtons times meters. Well, newtons times meters is going to be joules. So then I'm going to have 320 joules. Okay. And now to calculate the additional work, again, I'm doing WF minus WI. So I'm going to do 320 joules minus 80 joules. So the additional work is going to be 240 joules. Okay. Now, what about the force? So I'll use a different page for this now. So the force, again, we're just going to use K times X. So then our K value, again, is going to be the one from part A. So I'm going to have 4,000 newtons per meter. And the spring is being displaced 0.4 meters. So X is again 0.4 meters. So then my answer for the force is going to be 1,600 newtons. Okay, and then that solves the problem.